right, let's make a start. So this is just for the new camera. This is also streamed widely on YouTube and Zoom. So hello to the virtual audience and hello to the in-person audience. So today we have two talks. The first talk is now given by Peter Schmid, and the second talk will be given by Ricardo Inueza at 2. So Peter is a professor in mechanical engineering at the King Abdullah University of Science and Technology, KAUST, and he's going to give a tutorial and talk about data-based reductions and closure models for dynamical systems.
Okay, all right. So let me first start out by thanking Luca and Kartik for organizing this. It's very enjoyable, lots of good discussions and lots to learn. So I also want to, before I start, acknowledge the collaborators. It's going to be split in two, but the collaborators are George Ricatz, who was here earlier this week, and then Florence Marcotte and Yannick Ponty from the Université de Côte d'Azur. Right. So as I said, this is going to be a two-part talk. There will be some connections, but definitely you will see a change in gear as I go from number 1 to number 2. The first one will be database reductions. We're going to use transfer operators and plenty of graph theory that will help us find patterns. And that one is the part that I do with Florence and Yannick. And the second one is something that George and I started at the last CTR meeting in summer of last year. And that one is closure models for dynamical systems, and that one is using memory kernels and machine learning. All right, so let me start with the first one, database reduction. So database techniques, they have somehow joined everything else that we do for fluid analysis and fluid simulation. So they joined simulations and experiments. Both of them generate a lot of data, and the question now is that what do we do with all that data? How do we get the essence out from the data? So we're trying to find patterns, sub-processes, break it apart into a hierarchy of processes. And the more complicated the flow and more multi-physics the flow is, the more important these techniques become. But database techniques are always somehow contrasted to model-based techniques, as if it's almost like saying that database techniques don't have a model in it, but there actually is an underlying model in it that we have to somehow assume or at least hypothesize. And the database techniques address then the issue of recovering the model parameters of the model that we actually underlie the data as we observe the data stream. And that one goes back all the way to system identification where things have been done like this. So this is somehow the quintessential starting point of database techniques is actually system identification. Now, of course, there have to be changes, choices to be made. The chosen model that we have or hypothesize has to reflect all the main features that we have in the underlying flow. All the things that we're interested in, whether it's acoustics or chemical reactions, they also have to be part of that model, obviously. And on top of that one, we also have to have supplementary constraints. And that's where conserved quantities, for example, come in, symmetries come in that have to be imposed as we stream through the data. So it's a little sketch down here where we have the model with some kind of parameters, and we're going to stream through the data, and then we impose the constraints. And there's choices that we have to make. For example, the model by itself, we have to make a choice whether a linear model will do, whether we have to go to a nonlinear model, whether we want to throw a neural net into the model equation, and then get the parameters out. Also, for the constraints, this is where the physics-informed models come in. We want to throw as much into the model as we possibly know. Also, symmetry awareness comes into the constraints. So Beverly showed us yesterday about the symmetry, the physics-informed DMD, where you have certain constraints. And what that one does is it basically brings us onto the manifold. We don't optimize and find the optimal parameters all over the place. We actually restrict our search space to certain regions of parameter space that observe all our constraints. Also, we have to decide on the data that we observe and where we observe it. So here's a choice to be made between physical space. Sometimes physical space is too high dimensional. Spectral space, often operations or processes in physical space look very, very simple in spectral space. Sometimes it's easier to identify a dispersion relation rather than a PDE. Okay? And then one that is a little bit neglected, at least in my view, is the phase space. I'm going to show you how to do that today. Then we also have to somehow also decide on the learning. How do we learn these model parameters? Are we doing a fitting? Are we doing a regularized fitting by enforcing other things onto the model that are not necessarily physical or symmetries? For example, we want to have a sparse model. That one goes on top of that one. Or if we include uncertainty, the learning can also be done within the Bayesian framework. So there's a lot of choices to be made. And the one that I want to talk about today is a formulation in phase space. So that's what we're going to be in phase space. Why are we doing phase space? It has an advantage that, following what Karthik said, we're going to look for linearity of a propagator in phase space. And we can do that by doing a high enough dimensional embedding in phase space until a nonlinear process looks linear in a high enough dimensional space. So this is like the Koopman idea. The other thing that is good in phase space is we can actually have multimodal distributions. So many times when we do a model reduction, we go through an SVD or a POD, but a POD is basically fitting to our data a hyperellipse where all the major axes are basically variances in certain directions. But if you have a non-modal, a multimodal, or a bimodal distribution, that one is a very poor match, right? Because the fate of the system basically goes through certain regime changes where it's in one state for a while, and then it switches to another state for a while. If you fit all of that one into a hyperellipse, you basically fit something that is never observed. So this is also good in phase space, and we will see an example today where we have actually 4 different attractors in phase space, and that one is done quite nicely in phase space, which would be a little bit harder to do in any other space. There's of course a disadvantage also for going to phase space. Phase space is very, very high dimensional. And I'm going to show you a little bit later what to do about that high dimensionality. The model that we're going to pose in phase space is a Markov process. That one is stochastic. We will see where that one comes from. But this one leads basically to a Frobenius-Perron transfer operator. So just to give a little bit of a map where we actually are on this one, this is basically what we're doing. So here we have our dynamical system, and we can distinguish between a primal way of doing things and a dual way of doing things, the direct one and the adjoint one. If we go discrete, which means basically just snapshots of our data, that's more or less what we do. On the primal side, you get the Koopman operator, and the Koopman operator is basically the discrete version of this continuous process, which is an evolution under the flux, under the flow of the dynamical system of some observables. So this is the discrete version of this continuous process. It's an evolution equation of observables, and that operator is called the Lie operator. The Lie operator is the continuous equivalent of the Koopman operator. On the dual side, we have the Frobenius-Perron operator. In that case, we're not actually propagating observables, we're propagating probabilities. And that one is now the Liouville operator, is the continuous equivalent of the Frobenius-Perron operator. And in this case, it's not an evolution equation. Well, it is an evolution equation, but it's a conservation law. And you see that they're nicely related through primal dual operations. If I multiply this equation by a probability and integrate over and bring everything over to the other side with a variation in phi, in the observable, I exactly get this. The grad turns into the diff. Okay, so nice equivalence between the primal side and the dual side. Now, where we operate here is over here. This is what we actually approximate. So keep that in mind. It's an evolution equation of probabilities under a flux function f that comes from our dynamical system. Of course, we don't know that. We need to approximate that one. But by observing the data, can we encode the f into the evolution equation for rho to get an evolution equation for the probabilities through the Frobenius-Perron operator.
It's like a Fokker-Planck equation.
This is the noise-free version of a Fokker-Planck equation. Exactly.
One more related.
Yes.
Yeah. Is this related also to the master equation?
Yes. Yes.
It is the master equation.
Yes. This is the master equation.
But written in the differential form.
Exactly. Written in the differential form. Yes. Okay. So here we go. We have to overcome the high dimensionality, and we're going to do it first the cheap way and a little bit of a crude way, but then I'm going to go back a little bit later and show you a few other techniques that we can use to reduce it. But sort of bear with me for this one here. So we're going to boil down the high dimensionality by using reaction coordinates. And the reaction coordinates are basically coordinates that capture the main features of the flow that we wish to analyze. So for example, if you have a turbulent flow, your reaction coordinates could be some kind of an integrated kinetic energy, the mean flow, the integrated dissipation. You can even partition that out in certain regions, closer to the wall, further downstream. Entropy, minimal channel units. We've seen, I think, a 9-dimensional system from Bruno Eckhardt. That also is some kind of a nice way of reducing down to very few reaction coordinates. If you have any other application, I'm going to show you one on the next slide, you often get away with average quantities or higher order statistics. Okay. So this is a very, very simple way of first boiling it down to something that is manageable. Okay. And then once we have that one, we go through the full analysis, and then we're going to go back and say, and revisit that one a little bit later. The specific application that I want to talk about is the one that they do at the University de Côte d'Azur, and that one is a magnetic Taylor-Green model, and that one is a substitute for Earth magnetic field reversals. Okay, so you have the Earth magnetic field here. The North Pole is where we usually have the North Pole, where we used to have the North Pole, but that hasn't always been like this. The North Pole actually is off the magnetic North Pole. It's often, where the South Pole is, or very close by. So this thing reverses on a time scale of about 10,000 or 20,000, 25,000 years. And you never know when the next one is coming. Apparently, we're close to a switch. That's what I'm told. So hold your horses. So the Taylor-Green model is basically a small box. It's a small periodic box model that shows reversals. Okay, and this is the Gavini equation. We have a box, periodic box, very much like HIT, 64 cubed. These are the hydrodynamics equation. You see here is the Lorentz force. That's the only thing that we have on top of that. And then we also track the magnetic field, has an advection, has a shear, and dissipation here. And then, of course, you have mass conservation, if E is U, and you have no magnetic monopoles. That means the divergence of the magnetic field is equal to 0. And then here, J is just the current density. Okay? Now here, there is an F that makes the whole thing work. And the F for Earth, if you would have an Earth simulation, this would somehow model the constant forcing by buoyancy and Coriolis forces that gets the whole thing going. If you have a dynamo in a little lab, you have to somehow force it artificially from the wall. But this one is basically modeling what the Earth is doing through buoyancy and Coriolis. Okay? So if you do this one, if you solve this one in the box, this is more or less what you get. And now we already have reaction coordinates, and our reaction coordinates are the mean fields of the velocity in x and y and the magnetic field of x and y averaged over the bottom eight points of this box. Okay, there's some symmetry constraints. There's a reason why we do this, but that one goes a little bit too deep into the details. So this is our magnetic field components in x and y. The magnetic field component in Z is much, much, much lower. So all the switching is basically done by left and right in the Z normal plane. There's not much that goes up and down. Okay? So if we watch this one, the Px and Py averaged over this blue box, this is what you get. The green one is dy, and the blue one is dx, and you see that they're going up and down and up and down. This is maybe not as nice as the next one, where I do a quadrant analysis. So I have 4 quadrants where bx and by are both positive, where bx is positive and negative, all the 4 quadrants. And if you look through this one, you definitely see this kind of regime switch. Okay? Up and down, it goes to one quadrant, then it switches to the next, and so on. And you never know where the next one comes. All right, so if you plot bx versus by now in phase space, so we're going into the magnetic phase space, it's usually 4-dimensional because we also have a Vx and a Vy, but this is just a 2D slice through the V phase space. This is more or less what you get. You have the 4 quadrants, and this thing moves around, and already to the naked eye, you already see that it clumps a lot more here and here and here and here. So if you would do a PUD analysis of that one, that doesn't go very far, okay? Because it's clearly hanging out more here. So it's a quadrumodal distribution where we have 4 metastable states with long residence time. So it sits here for quite a while, and then it's connected by transitory routes. These are the red ones that get us from one to the other. But you also see, for example, that it always takes the same path. So it looks like it goes up and then down, up and down. Here it's also up and down, up and over, and here it only does it once. So you can already see we don't have a long enough record for this one. We would actually sample a lot more. Okay, so these are 10,000 snapshots, but we need probably by 100,000.
Yeah, just to get the framing right. So
yeah,
the mean fields are averaged in Z.
The mean fields, no, it's averaged over the entire box. It's one value over that entire box.
Okay, so you have it's a 4-dimensional average.
Correct. But this is only 2D slice. The magnetic part is the one where you actually see the switching. The velocity doesn't do as clear a switching as this one. It follows the magnetic field, but it's much clearer in the B field to get the 4 metastable states. Yeah.
It's showing it can only go one step.
Exactly. Very nice. Yeah, it doesn't go through the thing. This thing in here is the transient in the beginning. So if you go back, we're going to actually exclude that one. If you go back, this is basically this little thing here that sits right in the middle, and you know you need to kick it off before it goes into its motion.
How about the BZ?
BZ is very much smaller than this one. This one goes from -1 to 1 in non-dimensional coordinates. The BZ is 0.02 or something like that.
You don't have paths going.
No, not much. Okay. All right. So what we actually do now is we take this phase space here. Of course, it's 4-dimensional, but now we only plot it in 2 dimensions. And we're going to discretize that one. We're going to discretize the phase space into uniform hypercubes, and these hypercubes are 4-dimensional phase space. So to avoid the curse of dimensionality, because there's about, if I discretize each phase space direction in only about 10 or 20 points, I get an enormous amount of little hypercubes. But we're going to make the assumption that the manifold on which the phase space actually goes around is very much sparser than the entire number of boxes that you have. And you see later on, I think we have 1,700 boxes that are actually needed to represent the phase space dynamics over 1 million boxes that are possibly in that high dimensional phase space. But to avoid the curse of dimensionality, which would we have by just dividing the subspace and discretizing in a blind way, we're going to assign a hash value to each visited hypercube. So every time we track the trajectory, and every time it goes into a new cube, we start that new cube only once it's visited. And it gets a label, and that label is kept in a hash list, so that once that thing comes back to the same box, we know that we already have that box. We don't introduce a new one. Okay. So this is the idea of discretizing this one along the trajectory. And the algorithm is very nice because it scales with the number of snapshots rather than with the dimensionality of the problem. This is the way we avoid some kind of an exponential runaway of the problem. We use double linked lists to retain full information, so each box has both knows what snapshots are in that box, but also every snapshot has an address that knows I'm in box number so and so. It goes both ways. So full information to the trajectory and the dynamics. Okay. So, yeah.
Why is it number of snapshots and not number of boxes?
Ultimately, it's a number of boxes, but the discretization, until you have the full boxes that you need the number of snapshots. So now we have to go back to our conservation law. This one was the continuous version of the Frobenius Perron operator, which is the evolution of probability density. Okay, so this is the Liouville equation. That one defines the flux of the probability across a box boundary. So if you actually do a propagation operation integrated over one finite volume in phase space, this is what you get. So the propagation of the probability density integrated with a certain probability measure over one grid cell here, that one is 4-dimensional later on, should be the same as the probability that you had one time step away after your volume is basically propagated back in time and deformed. Okay? So this is S getting us from here to there, S inverse getting us back. So this little piece here moved into the A. Okay? So now we want to have a transfer operator that maps us from here to there, discretized in our finite volumes. This is equivalent of solving this conservation law by Lagrangian tracking of a probability measure. Okay. So this is the equation that we have, and this is actually the textbook definition. This P here is the textbook definition of the Frobenius-Perron transfer operator. Okay. This is the continuous way of doing it, but discretizing finite volumes. And now we need to somehow make it more practical. And the way we do that is we compute the probability of finding a snapshot in box BI that has been in box BJ one time step earlier. Okay, that's the S minus 1. So this is more or less doing a finite volume discretization where we go over the face of a finite volume with a flux function. If you do a row flux, for example, that's exactly what you do, or Wayno. So here we have it. This is the discrete version of this integral here that defines Pij. Now this one is discretized in terms of I and j boxes, where we have a probability measure of finding something in the box Bi that was one time step back in box Pj, divided by all trajectories that end up in Bi. Okay? So if this is I and this is the choice of j, basically taking this little red piece and evaluating that, because that one will end up in here. And the probability of going from here to there is given by the area of this little red triangle divided by the area of the green one. Okay. So this is a discrete finite volume version of a conservation law in phase. Now, here in box, yes?
I see that you're actually tracking S. You know, Lagrangian amount over time too, right?
Yeah.
Is it possible to do this or that even better so that you can track the elements from one box to another instead of?
Yes, I'll get to that one. I'll get to that one. This is the Lagrangian way following a trajectory. That's database. That's the more data-based approach because we already have the trajectory. But there's also an Eulerian way where you seed particles in one box and let them evolve. Okay, that would be the Eulerian approach. Yeah. Both ones give the same. Very good question. So the box size, of course, is very crucial here. This is the discretization. So the box size choice, if you have small boxes, you get a very good resolution of the trajectory in phase space. So phase space is discretized very, very nicely, but you get a poor statistics because not very many trajectories end up in a small box. If you make the box large, then you get a good statistics because you have many sample points in the box, but you get a very coarse, phase-space dynamics. Okay? So the heuristics here is that you should actually only go over one time step you sampled into a neighboring box and not jump too far, which is the equivalent of a phase-space CFL condition. Okay? So it all comes in quite nicely if you think in terms of finite volume. Also, this one also is related to a little bit like particle image velocimetry in phase space, because what we're actually doing here is we have two snapshots, one but with one time step apart, and we do the correlation of this one in a statistical sense. So in that sense, we're doing like PIV of a phase space trajectory, where the velocity is the transport rate of the probability. Okay? You can think of it in many, many different ways. And of course, with all these counting and following the trajectory, what we're actually doing is in P, we encode the dynamics F. So the F gets somehow magically encoded into the P. So the P has the full dynamics of our trajectory in phase space. Okay, so this one is actually a very well-known technique. Has been done before with cluster-based ROM by Kaiser et al. And that one is called the Ulam-Galerkin method. And here comes what Sam said. If we do it data-based, we just follow the trajectory and see what kind of boxes it traverses and build our P this way. Okay. The Eulerian way of doing it, but for that one, you need a model. Okay. You need a model because you seed one point, one trajectory in every single box you have, and then go one time step. So you either do it once for a long sequence or many initial conditions in the seeded boxes and go over one time step. Okay, a little bit like how you do Lagrangian coherent structures. Very, very similar to it. Okay. Okay. So once we have the P constructed like this, what can we actually learn from P? Well, P is row stochastic. That means the probability has to add up to 1. So if I look what every box contributes to another box over one time step, this has to add up to 1. Okay? So it's row stochastic. That makes it a Markov process. Okay? Once you have a row stochastic matrix, it has one unit eigenvalue. So the biggest eigenvalue is 1. And that one is the stationary distribution, okay, in phase space. So you get a distribution of where things hang out most likely in phase space. That's the stationary distribution. Pi times P is equal to pi. Now, with Markov chains, they always multiply from the right. It's just how they do it. We multiply from the left, they multiply from the right. That's why it's row stochastic and not column. Okay, the next eigenvalues are more interesting because then we go down. The next one is less than 1, because 1 is the biggest one, that's always there, less than 1, and that is a distribution of persistent states. So the stationary distribution has a residence time of infinity. The next one down has a residence time over 1 over the eigenvalue, or 1 minus the eigenvalue. Okay, so if you have something that is 0.999, that one is a is a state that hangs around for a long time. Okay, so this way we actually separate out the dynamics into persistent states that you see very often. That would be our 4 states in the corners. And then the small eigenvalues correspond to transitory states that make the fast switching. Okay, and the associated eigenvalue point out regions in phase space where this action appears. Okay, so how do we go from there? We can further break that one down, not just doing the eigenvalue analysis, but we can further break it down into sub-processes, because we saw that there's 4 little patches in different corners of the phase space. How do we get these patches? Okay, how do we break it apart into sub-processes? So what we do is we take our P matrix, the Frobenius-Caron discrete version, okay, and we're going to interpret that as describing motion on a graph. So now every box is now a point on a graph, and we're going to move around. So we have a random walk on a graph where each link between a graph node and another graph node is given by a transition probability that we calculated from Pij. So this is just a random walk on the graph. And P acts as an adjacency matrix for an associated graph. So all these boxes here now are points on the graph, and the links are the transitions between one box and the next. And this loop here is you stay in a box over one time step. So that's what you have. And now we can, suddenly it's a graph problem. And now we can put all the stuff out we know about graphs. So for example, we can compute communities. We say which nodes actually just do little loops or exchange mostly between themselves, but never go to another corner of the phase space. This is the way we separate out coherent structure that belongs together. And that one is community computations. We use this algorithm for that. Once you have all the communities, you can actually lump them together even more. I'm going to show you why that is needed and then how it's done. And then the really exciting thing that we haven't gone through yet, but this is just sort of future work, that one is compute transition probabilities. I'll get to each one of those on the next slide. Okay. So here is the community calculation. So this one, we use a Louvain algorithm. That's a very standard algorithm for doing community clustering. So it's a greedy algorithm that maximizes modularity. And modularity is a measure of what belongs together, what acts the same, what lumps together, what is a clique, basically, in a social network. Okay? For example, if you have Twitter and you see that, oh, there's a community that just exchanges among themselves, but doesn't interact a lot with other communities, then you say this one has high modularity. And high modularity basically means it identifies strong intraconnectivity within the community, but very weak interconnectivity to another community. Okay? This is the definition, the graph definition of coherence. Okay? So, yes?
You know, to have a Markov chain, will be an idea to spectral clustering.
That is spectral clustering.
Not Louvain exactly, right? Spectral clustering would be combine the Laplacian and look at the.
Yeah, you can do it with a graph Laplacian too. Yeah, it comes out about the same. We implemented also Leicht-Newman, which is spectral clustering.
Right.
It's the same.
Very
little different.
Maybe you can do some connections that are exact with the eigenvalue that you were mentioning before.
Yeah, we could do that. We could experiment with that one. Good. So the outcome of this algorithm, once you do that, is a matrix Z, where here you have the box ID. Okay? So these are all the boxes you have. Each row is a different box, and then each column is a community the box belongs to. For example, all these boxes belong to the same community. These belong to the same community, and so on. It doesn't have to line up as nicely as this. It could be all sprinkled all over. Okay? But this is basically a way of sorting. And once you take this Z as a similarity transformation, you basically do a deflation or agglomeration. That's exactly what you do when you do multigrid. When you do multigrid and go for the coarser solution, you restrict, right? You lump things together, and suddenly a collection of small boxes becomes a big box. Okay? That's exactly what we do. So this one is basically an agglomeration of the graph, where we're coursing the graph, or we coarse grain the graph by lumping nodes together that actually are strongly connected. Okay. So if you do this with the adjacent,
Strong connection is geometry.
No, it's because of the probability of transition.
Even though they may be different locations.
Yes, they will come together. Yes. Well, they are close together in phase space, right? Because they're connected through the trajectory. So there's nothing that jumps from here all the way to a phase space over there. So there is a geometric encoding from that is given by the trajectory. So this is the adjacency matrix of the raw one. That one had, for example, 500 boxes. And then you hit it from both sides with these Zs, and you do it over and over and over again until nothing changes. And then you see how it lumps together here. And once we have it all lumped together, we can actually see that, for example, this community here, this one exits only through cluster 1. That's the only way to get out of this box here. Cluster 1 then goes into community 2, but this one doesn't stay there. It has a very, very small resting probability. That's why there is no point on the diagonal. So it goes right back to community 1 through cluster number 10. And it ends up in cluster number 2. Okay? So you can actually see these loops in this graph that do exactly the excursion that we say. You know, we go from community 1, we go really fast out, we don't stay there very long in this one. So this is a transitory state. And then we go back and come back to cluster number 1, community number 1, sorry. Okay. So out of this one, you can learn a lot about loops and the dynamics in phase space. So if you do this one for our B matrix and you cluster it out, this is more or less the communities that you get. They look like they overlap a little bit, but remember, this is a 2D projection of a 4D problem, right? So there's actually 2 more layers on top that get squished down once I project onto the X and Y. And this is the corresponding cluster graph. Okay? So you see already this one is nicely clustering the dynamics. So the next thing that we're going to do is, this is a greedy algorithm. And the greedy algorithm is just an approximation of what we really want to do. Right? Because the breaking up into a community is an NP-hard problem. There is no solution, no polynomial algorithm that gets you there. Right? So this greedy algorithm more or less does as good as it can, but it gets stuck in a local minimum eventually. Right? You cannot get to the true one. So at some point, this modularity fizzles out, and we're going to left with, you know, a lot of clusters that don't combine anymore. Okay? So what we do next is we take the communities as they come out from the first part, and then we do what's called a minimum spanning tree. So let's say these are the clusters that come out, and then we're going to have a connection of every point such that all the nodes are connected, but this connectivity is as cheap as it gets. Okay? That's called a minimum spanning tree. It spans all the network, but it does so by doing it as cheaply as possible. Now, what does it mean cheaply as possible? We want to cluster this one, not as cheaply as possible, but as likely to stay as possible. Okay? So instead of a minimum spanning tree, we would actually need a maximum probability spanning tree, so that everything gets lumped together that has a high probability of staying within the same clusters. Okay? So in that case, we actually have to take the complementary transition probability. If this weight here is 0.2, we have to change it to 0.8, 1 minus. Okay? The probability of not going there. Okay? So if you do this one, then you get a minimum spanning tree, and then you actually look at all these links here, and you take the maximum weight on this link, which is the least likely probability of going on that link, okay? And you're going to cut it here. Okay? And then you have 2 communities. And you cut it here by cutting out the max cut, but remember this is complementary, so this is the least likely probability of going from here to there. Okay? And this way you can even cluster more and more, but now you're in charge of how many clusters that you want. Okay, so you get a hierarchy of communities. So if you do this one with our thing that came out of the step number 1, you actually get a nice minimum spanning tree. Then you cut all the unlikely ones. These are unlikely. We knew that this was a transition state, right? These are cut, and then you get nice clusters here, 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 and here. Okay, so it does exactly what we need to do. All right. So and then this is the reclustering. After you've done the Louvain algorithm, then you do the minimum spanning tree max cut, and then you get this nice structure from the transitory states actually break into 2. They can be lumped together if you keep on count. So this works quite nicely for our Taylor-Green vortex. And then the last one that I said, this is future work, but this is the next step that we want to do. And that one is, of course, we want to ask the question, how likely is it to go from somewhere here to somewhere over there? Okay, what is the most likely path to go there? Okay. And of course, this one is the shortest path problem. Okay. We want to go from here to here in the cheapest possible way. And that one is a classical shortest path problem in graph theory. So if you do a class on networks, this is probably the first thing you do. You go from A to B. This is what your car does, or your car navigation system does. If you type it in, you want to go from A to B. It does a Dijkstra algorithm, and then it tells you the shortest path to go from A to B. That's exactly the same thing. But now we do it, we navigate through phase space, and the cost. What means shortest path, right? Short doesn't mean anything. Short means the most likely one to go from here to there. So you want to have the highest probabilities to go from here all the way to here. Okay? What is the path that you should take? And that's the one you probably most likely see. Okay? The statistical argument. So what that means is this is known as instantons. You calculate instantons from optimal transport between some state of a dynamical system to another state of the dynamical system, and you say which is the best way of going from here to there, using all instabilities, whatever you have at your disposal, to get from A to B in the cheapest means most likely probability, from a probability point of view, most likely manner. Now, there's a little bit one needs to change, because Dijkstra's algorithm is additive. Okay? So Dijkstra just says, okay, from here to there, I sum all the costs of each piece of the road to go from here to there. Okay? Well, if we go from here to there, it's a multiplication by a Markov chain, so it's multiplicative. Okay? We multiply by the probability of ending up as we go on the piece of the road. So to allow Dijkstra to be applied to that one, we have to take the negative logarithms of the transition probabilities. Then we turn a multiplicative path into an additive path. And then we can use Dijkstra on the logs, the log of the probabilities. Okay? To go from here to there. And that one gives you the most likely path. So this is still work in progress. Maybe next week or 2 weeks, or who knows when, I will report on that one, how far we go. All right. So this was part one of the talk. So let's now change gear a little bit and talk about closure problems in dynamical systems. And that one is joint work with George Rigas. Okay. So the closure problem is somehow a key issue. Every time you do a model reduction, you somehow have to decide of what you keep and what you throw. Okay. So, but the influence of the retained scales is very, very important. The influence of it's actually the other way around. The influence of the dismissed structures on the retained ones is very, very important, because that one decides on the stability of the system that you actually keep. So for a proper closure, we somehow have to throw in a model of all the dismissed scales. So we do that, for example, in turbulence simulation by a subgrid scale model. All the things we cut out, we somehow have to replace by a forcing term that more or less mimics all the entire influence of the scales that we threw out on the scales that we kept. So this is usually what we have. We have some scales that we calculate, that could be POD modes or something, that we retain, and the other ones that we dismiss. We're going to call it R and D. And the truncation point, I also want to point that out. This is an issue of discussion, maybe a little bit later. And that one, that the truncation point is often selected by energy arguments. So we say these are the singular values. We're going to get 90% of all the energy. We're going to that's good enough. 90% is a large number, and then we just cut that. But what it really should be based on is a sensitivity argument, because, for example, if you go to aeroacoustics, something that has very, very little energy can actually provide a feedback loop that is weak but has high receptivity on something that is actually important. So the energy pathway can actually pass through a low energy state and then come back with a high receptivity and a high sensitivity to a high energy state. Okay? And this one would not be modeled by just energy argument. But that's a topic for another day.
Are these two things orthogonal, you think?
No, not necessarily. I don't think so.
Okay.
We talk about it later. Yeah. So feedback loops can play a key role, and that one is a feedback loop through acoustics, a feedback loop through electricity, right, which is spreading everywhere. It can be a feedback loop through recirculation, flow separation, and things like that bring information back. But let's put this aside. Let's say we know where we want to truncate. Okay. So the standard technique then is we're going to use we're going to project onto our retained states. So this is our transpose. And we're going to reduce our large system into a small system, DDE of a few coefficients. And that one automatically partitions our evolution operator into a retained to retained, retained to dismissed, dismissed to retained, and dismissed to dismissed section. Okay. So it automatically partitions this one out. Now, if we do a linear example as an exercise, okay, this is what we have. We have the retained scales and the dismissed scales. And then this one is a linear one now, ARR. So this one is the part that does the retained talking to themselves. This is the driving from the dismissed ones, and here's the dismissed equation. Now you can actually solve that one using a Schur complement. And the solution to this one is actually this equation here. Okay. And it's a self-contained equation. That means it only depends on R. So the D is totally gone. We solved this one, in a sense, we solved it. The solution is right here, very costly. Okay. We solved the second equation and stuck it back into the first equation. Okay. And now everything is in terms of R. But what it turned into is now not a differential equation anymore. It's an integral differential equation. It goes from 0 to t, and it has R that goes back in time. Okay? 0 to t. So it seems like what we bargained for is a memory integral. Okay? So it's important to keep the memory of our retained scales to make sure it's properly closed. So if you look at this one, this is actually what we usually do. This, when we cut it here and neglect all of this one, this is the truncated system. We project, we truncate, we run with it. This is the residualized system. This one is the full solution. Okay? There's nothing thrown out. We just have to haul along this term forever. Okay? And then this one here, this piece here, is obviously the influence of the dismissed scales onto the retained scales. Yeah, exactly. There should be an initial condition. That's true. Okay. So this is from Kartik's paper with Ayub and Eric. So this is a simple example where you have a dynamical system, and the yellow part is basically the contribution of the memory term. Okay, that integral part of the integral differential equations. And you see that if you neglect it altogether, you get the red curve, and that one is way off from the blue curve. What you also see that is very encouraging is that you don't need to go all the way back in memory. The memory is actually quite small. Okay? After a while, it forgets. Okay? And this is the saving grace of this type of approach. You need memory, but you don't need all that much memory. Now, this technique has been known for a while. That one is, for example, that you need history terms or memory terms in system identification. For example, if you do a max system from system identification and you change into an RMAX system where you actually remember the output one time step back, just one time step. This alpha here makes a huge difference. And that one is very, very similar, and RMAX systems work much, much better than MAX systems for dynamical purposes. So let's look at this term here. This is the one that we have to deal with to close out properly a dynamical system. So here is our retained scale. That one is usually low dimensional. So the first part here is low to high. Okay? So this one gets us back onto the dismissed system. Okay? Then this one is high to high. This is the evolution operator on the high scales. Okay? This is basically the costing part inside. And then here we're going to boil it back down from high back to low, because this is the driving term for the low dimensional system. Okay? So if you go low to high, and high to low, if you add it all together, this one as a composite operator is low to low. Okay? And this low to low is more or less a kernel. This one can be replaced by a convolution. So this one is the kernel. And the kernel, now the question is, can this kernel be identified or learned? So if you have, can we identify the kernel from data sequences? So if you do the linear part, if you do the linear case, then the kernel, if you spell it out, if you write down the equations for the kernel, this one leads to an upper triangular block tuplets matrix. It's a mouthful. The tuplets comes from being the same kernel over every time step. So the kernel doesn't really change. That's why it's tuplets in time. Block, because it has high input and high output. Okay, so it's a block matrix. And upper triangular because it's causal. It goes from 0 to t, but it doesn't go into the future. That's why it's upper triangular block tuplets altogether. Now this one can be nicely identified by a manifold constraint optimization, very similar to what Peter Badu was doing with Beverly. So you have a constraint Probustus problem where you shoehorn the solution into a certain admissible solution state. Okay? And that admissible solution state is upper triangular block tuplets matrices. You only optimize over that group of matrices. And that one can be done nicely with this nice, I think it's a MATLAB library, ManOpt from around here, Sepulchre, on the engineering department. This is the linear case. There are a few alternatives, okay, of getting memory information into the identification of the kernel. The first one is take snapshots in higher dimension by time delay embedding. So this is taking snapshots and stacking them underneath, okay, and have, instead of processing the snapshots by themselves, you process little movie sequences of the snapshots. Okay. So this one basically traces out the yellow area of Cortex plot. Okay. If you cover a long enough sequence, you actually capture memory effects. So this one goes into rel patterns, embedding HAVOC, tantalized DMD, and so on. Okay. Recently, so this improves predictability, stability, but at the cost of a higher dimension. This thing becomes pretty big if you stack it all up. Okay. So recently we've been playing, and we're very excited about a technique that is locality preserving compression. Okay. So the question is, can we reduce the dimensionality of the problem while maintaining the relational distance in time? Okay. What do I mean by that? So we want to compress our snapshots in space to get around the high dimensionality. We don't want to stack, we actually want to compress, but under the condition that the dynamics is not messed up. Okay? So that is the question of that we ask. And there is actually a technique for doing this one, and that comes from database analysis. So if you have a database, a big database, and it all has privacy data in there that you know, like medical records, for example, okay, that you don't want to give to anybody. But what you want to have is you want to have some kind of relations between all your medical records. You want to establish a pattern. Okay? So can you actually compress or hash all the information to take the privacy away, okay, but still keep the relational distance between all the snapshots? And that's exactly what we want to do here. Can we compress our space, but keep the relational distance between all the snapshots? The relational distance between all the snapshots is our dynamics. So if I take snapshot 17 and snapshot 37, arbitrary two snapshots, and I calculate the distance between them, and then I calculate that same distance from the compressed one of 17 and 37, that should be the same. Is there a technique that does that? And there is a technique that does that, and it works actually quite nicely. We can compress in phase space without distortion of the dynamics, and then we can analyze the compressed snapshots without curse of dimensionality and still get the dynamics, because if they're mutually as far away as they were before in phase space, that means they're so constrained, they preserve the dynamics. So this is a really nice technique. It's now applied also to Krylov vectors, because the Krylov vectors basically, through an Arnold, you get the eigenvalues, but if the distance of all the Krylov vectors is preserved, it doesn't matter what the vector is. So it's actually very, very nice. It speeds up everything by factors of about 1,000. Okay, let's go to the nonlinear case. If you have the nonlinear case, then machine learning comes in. Okay? So the question then is, can the kernel be modeled by an autoencoder? Okay? And that's what we did with George. But we want to learn from the linear design and see how that one carries over to the nonlinear autoencoder. So what that one translates, the linear design, if you remember, the kernel was actually 3 parts. There was low to high to high, and high to low. Okay? That was the linear kernel. Okay? So the nonlinear kernel will be something like this, but we assume, or at least we hypothesize, that if we have a structure that goes from low to high, and from high to low, this should more or less capture the same thing that the linear one would do. Okay? So we have the linear asymptotic limit in terms of shape. So that means we need a higher dimensional reservoir, like Luca, to accommodate the dismissed scales. Okay. So the way what we applied this one to was a closure for the harmonic balanced Navier-Stokes equations, A, B, and S. That's what George has been worked on for a while. So this is basically the nonlinear extension of the resolvent framework, where you have the resolvent. This is the linear part. This is the mean flow interaction. It's non-linear, but on the mean flow. So that means this is the linearized. It's linearized around the mean flow. Plus then you also have the crosstalks between the frequencies. Okay? So the nonlinearity is calls the frequency crosstalks. We're going to truncate this thing at some point. Okay? And then we want to model the effect of the dismissed frequencies on the ones that we actually keep. Okay. Linear dynamics, nonlinear dynamics. If you cut it here,
This one is exact.
this is exact.
Yes, and you don't know anything yet.
No, not yet. Not yet. It's coming. Okay, so let me show you the example for 4 frequencies. Let's say we want to keep 4. Okay. So this is the first one. This is the 0 frequency. There is no I omega because omega is 0. And then you have everything interacting into 0. So 1 and -1 interact into 0. That's this term here. 2 and -2 interact, 3 and 3, and 4 and -4 interact all into the mean. Okay? So this is known as the part that is mean field theory. Okay? And we don't go further than 4 because that's all the ones we keep on the positive side and on the negative side. Okay? So the next one here, this is the next line. Now the I omega comes in, L, and so on. This is the mean field again. And now we're going to interact into 1. And then we have 2 and -1. That together makes 1. -2 and 3, that makes 1. And -3 and 4, that also makes 1. Okay. But anything else would reach outside of the interval that we actually keep. Okay. So you get the idea. You do that for all the other ones. This is 2, 3, 4. And then we're done. So this one now has thrown things out because there would actually be other ones. For example, this one would have 5 and -2. That one we threw out. The -2 we have, but the 5 we don't.
Going back to the autoencoder, so basically it's an autoencoder that doesn't contract.
No, exactly.
It's an autoencoder
That blows up in the middle.
Now, right?
Yeah.
You want to get more
Yeah,
information.
yeah. So autoencoder,
information.
exactly,
All right.
exactly. You. That's the punchline. Yeah. So if you do this one, let's do this one again. Okay. But now this one is 0 for the truncated systems, and now let's keep the residual of all the pieces that come after that. So each one of those will not be 0. They will all have their own residual of all the frequencies that we did not keep. Okay. So we can formulate that one exactly like this. LL is low to low. So that's the ones from from -4 to 4. And then the high ones are all the ones that we threw out. So if you write this one, it's not a differential equation, it's an algebraic equation because we already Fourier transformed the way time in frequency. You get this partitioned matrix. This one is of course the small one. This in the corner is the big one. So if you extract the small one by using the Schur complement again, you can write this one as the residue. The residual of WL. Okay? The residual of WL based on that matrix is actually given through this one. It's the same technique, but instead of for a differential equation, we have it for an algebraic equation. So it's actually this one that is modeled by an autoencoder, and the autoencoder should inherit the relative dimensions of the linear, and that's the Morris-Swansea structure. So it should go high, it should go, this is even wrong. No. Low to high on this side, then high to high in the middle, and high to low on the left side. Okay? So we just carry this over as a way of the architecture of our autoencoder. Okay? So if you do this one is actually n is equal to 1. So the low ones are just 2 modes. So this is the mean, and this is the first resultant mode for one frequency. So we're not even keeping 4, we only keep 0 and 1. Okay? So the truncation is at 1. 2, 3, and 4 we don't keep, and 5, 6, 7, and all the higher ones. Okay? And then we have exactly what Luca said. We have low to high. So this one is now recovering all the things we threw away, okay? And that one has to be a higher one. And again, like we have with autoregressive equation models, we don't have to go really all that high. We just have to go a little higher to capture everything. We don't. This is not a restriction. So as long as this one bulges out a little bit, then and it captures everything that we need, we get a really good residual. So then we go from here. This is the recovery of the unresolved high ones. This is not the ones we calculated. These are ones that we recovered. And then from the high ones, we boil it down to calculate the residual on these 2 modes, and these are the residuals. Okay? Now, this one has been done with the full DNS. Okay? So this is our truth. And this one has been done with a net in the middle. Okay? So we go from low to high, from high to high, and from high to low. And this is the residual that we actually capture that is properly closing just a system of 2 frequencies. And this thing is remarkably close to over here. This one is fully recovered without actually ever having the high dimensions, or the high modes, the high frequency modes.
So when you say low to high, the low makes sense, U1, U1, U2.
Yeah. But
the dimension of the high,
yeah,
that's up to you, right? Like
that's yes, yeah.
You make it up.
Yes, exactly. Exactly.
So it's not,
yes. And that one goes a little bit into the length of the memory, right? How rich does that high dimensional space have to be to capture all the memory effects you get? You don't know. This is a parameter to play with. But we also did an experiment where we actually reduced this one down further and further, and it was pretty good for quite for as long as it's a little bit higher. So a little bit meaning this, I think this one was 40 in the middle or 20 in the middle. But then when you get down to about 10 for 2. Then it starts to deteriorate and then it collapses. So
it's not an autoencode, right?
No, yeah, we didn't. We had coffee and we cannot call this an autoencoder because it's an anti-autoencoder because it's bigger in the middle than on the sides. It's not the hourglass autoencoder, but then we didn't come up with any better notion, so we just called it an autoencoder.
What is the label data set and how do you train this autoencoder?
You train on the residual.
Okay, so on
Yeah.
the DNS.
Yes,
residual,
yes,
so
yes,
that's the label data.
yes,
So you
yes.
see the truth.
Yes, yes. Good. So this is it's an auto decoder. Yeah.
But it's not auto.
Yeah.
Because you're mapping.
Yeah,
It's not
you
identity
don't
mapping. So it's a function.
It's a function. Yeah. It's you don't go for the identity. Yeah. It's I don't know what to call it. Yeah. Autoencoder is probably the worst thing we could call it. Yeah. It's almost like an autoencoder but reversed.
A decoding function.
Yeah, a decoding function. But it works quite nicely, and you know, and if you apply this one to turbulence modeling, then actually the zero frequency should recover something that is close to a RANS, and then the higher frequencies should, you know, go into a hierarchy of RANS models. So we're trying to explore that one a little bit further with George. Yes, parts of it. Yeah, exactly. Okay, so let me sum up a little bit of take-home messages. You know, much can be learned from data sequences, as we know, but you have to be really aware that you have to pose the appropriate underlying model. I show you two examples. One was a Markov model that worked very nicely in phase space. The other one was an integral differential model that is better for closure problems. A phase space description is really advantageous. It has high dimensionality, so you have to worry about this one by choosing your reaction coordinates really careful. Of course, that also requires a little bit of physical insight into the whole thing. But if you can overcome this part, then a phase space description is very nice because it can deal with all kind of distributions. It can do rare events. It can do bistable states. It can do multimodal distributions like we saw for the 4 patches and so on. Once you're in phase space, everything that you know about graph theory can be more or less nicely harnessed. There's a lot more one can do in describing and analyzing the dynamical system, because then once you're on the graph with probabilities between them, you can basically go to town on the problem with, you know, pulling all the stops out from graph theory. There's a lot one can do about this. And if you, in terms of closure models, they are inherently non-local in time, but that one shouldn't come as a surprise, because that one confirms with the notion of coherence, right? If you have a coherent structure and that one moves and has an influence, you know, it has a memory of influence, right? So coherence in space with the Taylor hypothesis translates into coherence in time, and that one makes it linked. Okay, so having a non-locality in time is definitely something that is very natural, but that needs to be modeled accordingly. And if you do so, you do much better. All right. Sorry for going a little bit longer. Thanks for your attention.
All right. Thanks, Peter. Any question for Peter?
The reaction coordinate, so you pick that blue layer, didn't you just pick bigger layer than one?
If you pick the full one and you average over the full one, the average is 0.
It's gone.
It's gone. Yeah.
But what could bring you the other way? Why would a block of a layer?
You can also do, for example, a 32 by 32 by 32 cube. That one works just as nicely. Yeah. There's very little Z information. That's why we made it, you know, very pancake-like.
Right, but there's a dimension there.
Yes. Yes.
So you go to
Yeah.
average.
If I take a plane and average, I don't know. I'm still in the process of learning all the dynamo theory that goes into that. So I have to believe the people that gave me the data. Yes. Yeah, yeah. So eventually we want to replace these reaction coordinates by PUD modes that are actually localized in time and sampled in time. So we have a PUD description, like a 5-mode PUD description of each cluster. And then we switch between them. So that one brings a little bit more structure, spatial structure in there. Right now, we average everything out into one number. It does nicely for the splitting and all the intermittency parts, but we lose a lot of information by averaging, so all the spatial information is gone, but it's there. Of course, we always retain the snapshot. So if we say this cluster is important, or this cluster and this cluster interact with each other, we know exactly what snapshots belong to this cluster, so we can actually go back and see what it is in the data that it's doing. But we use a very coarsened version to first decide what's important.
Maybe following up on Jeremy's question, I'm not familiar with this model, but the 4 quadrants that you have,
Yeah.
Are they just kind of location in space? Or?
No, it's a magnetic field. It's a state of a magnetic field.
Is it rotation is symmetric?
It's symmetric within the box, but this is why we use the layer, right? It's not symmetric in that lower eighth, right? But over the entire box, it's symmetric.
So you are expecting a graph that's not symmetric.
Yes, yes. In that reaction coordinates, yes.
So if the follow-up question that is, so if you had 1/8 of this box that was used in place of physics, sure you maybe slide that over the box and what's this output?
You would get the same.
You get the same, like you kind of have your data so that you have more data. So that you can maybe
Yeah.
get, more information out of the
Yeah. The same simulation, you have more ensembles, more or less. Yeah.
I'm just curious.
That's a good idea. Yeah. Thanks. Yeah. Very nice.
Mentioning this technique to implement points in lower dimensional space. Is that in perspective?
Yeah. That's locality sensitive hashing. Yes, very nice. We didn't apply it to this one. We applied it to a turbo machine, and it gave us exactly the same modes in about thousands of a time.
I don't want to score the party, but about higher dimensions
Higher dimensions.
in your space space. All these techniques, what's the computational complexity?
Okay. The thing is, you can go to higher dimension because this goes by snapshots. The way we set it up, it goes by snapshots, not by dimensionality. So we're avoiding the curse of dimensionality. So we can go.
This finite volume type of technique there to do the transfer.
Exactly.
So
yes. The thing is, if you go to higher dimension, you need longer and longer time sequences to actually visit all your boxes. Right? So the higher dimensional they are, the more possibilities you have to go in certain directions.
I mean, higher dimensions in the past in the space, in your phase space.
Yeah, that's what I'm talking about. Yeah. No, that was 4 dimension, but I only plotted 2. The calculations were done in 4 dimensions: Vx, Vy, Vx, Vz, Vy.
Yeah.
So it's a 4-dimensional hypercube. If you go to 6 or 10 or 30 dimensions, you have to have longer and longer data sequences to actually trace out the manifold on which this thing lives. Right? So there is a restriction on that one. Going really high dimensional is probably not possible. You get faster.
How do you choose the 2 parameters, the Vx, Vy, and Ux? I mean, I guess in this case it's obvious.
The Vx, Vy, that comes out of the simulation, the magnetic field.
Yeah, but are these the proper parameters to drive the thing, or
well,
maybe there's another embedding, or
could be.
coordinates.
Yeah, could be better coordinates, but since we're looking at the reversals of magnetic fields, you know, the magnetic field is an obvious one to actually monitor. But you know, for turbulence, for example, if you look at bursts or something, or rare events like Fenix is doing, there could be other ways of describing, you know, better describing a rare event. High dissipation, high energy, something like this. So it is not hands off. You have to put a little bit of insight into the whole analysis.
Jason, sorry, go ahead. I was wondering when you translate the entire base space.
Yeah.
Do you happen then to discover also the dimension of your sort of factor? Is that correlated somehow with the Kaplan-York dimension?
You should. It's like box counting,
exactly,
right? It's box counting.
right?
Yeah. Okay. So the number of visited boxes to the number of boxes that are possibly there is giving you an embedding dimension.
Exactly,
right? We haven't looked into the box counting Kaplan-York stuff.
And it is a good thing because the system is dissipating, so you know that it's going to basically.
It's going to end up there at some point, and it just moves around and moves around. Yeah. But it will be nicer. This one was 10,000 snapshots, and clearly this is not enough for the discretization we have. So as we speak, actually, I know Yannick is running probably 100,000 or 200,000 snapshots.
Box counting is increasing.
Yeah, exactly. It's ticking away. I should have a counter here. Yeah. And then hopefully we do the same analysis, but with better statistics and smoother curves and a lot more.
Measure of your factor, somehow an approximation of the measure of your factor, like the probability measure. You have the moon example.
Yes,
right?
Yes. That was a measure, and we used a simple counting measure.
Okay. Right.
Yeah, a simple counting. Number of points that move in over one time step and divided by the number of points that are already there. This is all quite new. I just started this 2 weeks ago.
Cool. All right. And that would be the other question.
Oh no, you can have dynamos in cylinders too. Yes. Yeah. I don't know. I mean, a real dynamo only has two states. It doesn't have four. It's either up or down.
Yeah.
And this one, Taylor Green, is doing the same thing, but it has 4 metastable states. Right? So it's a model. It's like, you know, the Kuramura-Tsuda-Shinsky of dynamo theory. Yes.
Cool. Any final question for Peter? No. Okay. Cool. Let's thank Peter once again.